For a system, we can describe the macroscopic state by giving a macroscopic parameter of the system that corresponds to this state. For a given macroscopic state, we will find that there are possibly more than one microscopic states corresponding to it, and which microscopic states are allowed for the system to have in order to satisfy the restriction that the system is in a given macro state are basically the accessible states of the system. Okay, so first of all, if you give a complete description of a system of many particles, this basically defines the macroscopic state or macro state. Of the system. And we have external parameters that can affect the macroscopic state we will find the system in. So we will see external parameters such as magnetic field, electric field, the dimensions of the container of the system of particles. This can affect the energy of the system, energy levels of the system. So these are macroscopically measurable parameters affecting the motion of the particles. For example, we can think of magnetic field, electric field, the dimensions of the box that contains the system of many particles. These will affect the energy levels of the system. And given that you have a macroscopic state of the system, some initial conditions, this can give us, if the system is isolated, a total energy of the system. This is given with some precision in a range E to E plus delta E. And now if you look at the quantum states these particles can be in, so that the total energy is given with this initial condition, E to E plus delta E is the total energy. Those states will be the accessible states. So the definition of accessible states, the accessible states, these will correspond to quantum states in which the system can be found without violating the system restrictions. For example, for an isolated system, we specifying total energy in the range E to E plus delta E, so there is some precision to the specification. The external parameters of the system, will give us the set of accessible quantum states. So when we have a restriction on the system, so it has a total fixed energy E, or E to E plus delta E with some precision, we basically state that there will be some quantum states accessible to the system that will satisfy this requirement that the total energy must be E, and these states will be determined by the external parameters, which are macroscopically measurable parameters that are affecting the motion of our particles. So let's demonstrate this with two examples. The first example, consider an ideal spin system consisting of 4 spin 1/2 particles, each with magnetic moment mu sub 0. The system is placed in an external magnetic field B and isolated. The total energy of the system is minus 2 mu 0 B. List the accessible states of the spin system. So we are considering 4 spin 1/2 particles that are far away from each other but in fixed positions, so that you have no interaction between the spins. For example, something like this I'm showing you, and they each have magnetic moment mu sub 0 for each spin. This is for each spin. And we have an external magnetic field B that we're applying to this system, and we measure the total energy of the system to be minus 2 mu 0 B. What are the accessible states of the system? So I'm assuming that a magnetic moment plus mu 0, sigma is the quantum number we have to specify for the ith spin, is plus 1 when the moment is up, it's mu 0, and it's minus 1 when the moment is down, minus mu 0. So in order to have a total energy of minus 2 mu 0 B, I have to give you the sigma 1, sigma 2, sigma 3, and sigma 4 values. This is the quantum number for each spin that will satisfy the condition that the total magnetic moment M will be 2 mu 0, so that the energy will be minus m dot B. So I can write this as the dot product. Okay, so what are the states that will satisfy this condition? If sigma 1 is positive, it's plus 1. Sigma 2 is positive, plus 1. Mu 0, 2 mu 0, 3 mu 0, and then this one has to be minus 1, so that I will get a total of 2 mu 0. Sigma 1 can be positive, sigma 2 positive, sigma 3 negative, sigma 4 positive, sigma 1 positive, sigma 2 negative, sigma 3, sigma 4 positive, and then this one, sigma 1 negative, the other three are positive. So these four states, so if I count the states here, are the state numbers, state number 1, state number 2, state number 3, state number 4. Okay, so I can write this as a list of quantum numbers: plus, 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 minus, plus, 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 minus, plus, plus, minus, plus, plus, minus, plus, plus, and minus, plus, plus, plus. So I have a total of 4 accessible quantum states that will satisfy the requirement that the energy must be equal to minus 2 mu 0 b. And you can see that this energy is determined by the value of b. So the external parameter is setting the restriction on the spin system. So we have listed the accessible set of accessible states for this spin system. Let's consider one more example. Consider an ideal spin system A. So we have an ideal spin system A. There are 3 spin 1/2 particles. 3 spin 1/2 particles. It's ideal, so there is no interaction between them. Each with magnetic moment mu 0. So for each I will consider a magnetic moment mu 0. And there is a system A prime which consists of 2 spin 1/2 particles that are non-interacting, and these spins will have each a magnetic moment of 2 mu 0. Okay, the combined system A star is isolated, so it's A plus A prime, and it has a total energy E star, which is the energy of system A plus the energy of system A prime, to be minus 3 mu 0 b. So if I consider system A total magnetic moment, I can call this capital M, and for system A prime total magnetic moment M prime, then there's going to be the total magnetic moment of the star system, combined system, which is M plus M prime, so that the star system will have an energy minus the total magnetic moment, dot product with the external magnetic field B that we're applying to this combined system. And you should note that the combined system is isolated. So it is isolated, has a total energy minus 3 mu 0 b, external magnetic field B pointing up. So the thing to be careful about here is that each spin magnetic moment is 2 mu 0 in the primed system and mu 0 in the unprimed system. So I have to take this into account. Now, how many quantum states are possible in general for A star? So for A star, each spin consists of has 5 spins, and each spin can point up or down. So for 5 spins there will be 2 to the power 5. So the first one has 2 possibilities, up or down. The second one has 2 possibilities, up and down. And for the first two, the number of possibilities is 4. Up, 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 down, down, up, down, down. for example. And for 5 of them, it will be 2 to 5, 32 quantum states. Now, how many of these quantum states will be accessible states of the system? Okay, let's think about what should happen in order to get the total magnetic moment m star to be equal to 3 mu 0. So that means in order to get this total energy minus 3 mu 0 b, m star has to be equal to 3 mu 0. And I will count the states. I will give you the quantum number sigma 1, sigma 2, sigma 3 for the first 3 spin 1/2 particles. Sigma 1 prime, sigma 2 prime for the prime system. There will be a total magnetic moment for system A, total magnetic moment for system A prime, and a total magnetic moment of system star, which is the combined system. Now, in order to have a total of 3 mu 0, I can start thinking about this. So let's try the following for the first state. If sigma 1 is positive, sigma 2 is positive, and sigma 3 is positive, the total magnetic moment m would be 3 mu 0. So what I want for the prime system is to have no total magnetic moment. So I want it to have 0 moment, and this is possible if sigma 1 prime is positive, sigma 2 prime is negative. There is another scenario. All of these are positive. The first one is negative, the second one is positive, so that I will again get 3 mu 0 for system A and 0 for system A prime. So this is one possibility. Now let's think about what will happen if I have only one of these magnetic moments pointing up. So sigma 1 positive, sigma 2 negative, sigma 3 negative. This would give me plus mu 0, minus 2 mu 0, minus mu 0 as the total magnetic moment. In order to get plus 3 mu 0 as the total, I need to have plus 4 mu 0 for m prime. So they have to be positive. And as you can see, this plus sign can travel between the first spin, second and the third spins in the A system, so that I have the same scenario. So these two scenarios, number 4 and number 5, also give me minus mu 0, 4 mu 0, 4 mu 0. Now let's think about if there is any other possibility that will give me plus 3 mu 0. So I have considered all of them pointing up in the first scenario for the unprimed system, and one of them pointing up as the second scenario. So if I were to have two of them pointing up and one of them pointing down in the unprimed system, this would give me a total of 2 mu 0 minus mu 0 plus mu 0. Then I would need to have plus 2 mu 0 for the primed system. Is plus 2 mu 0 possible? Well, if both are pointing up, I would get plus 4 mu 0. If one is pointing down, I get 0. If both pointing down, I will get minus 2 mu 0. So there is no way I can get plus 2 mu 0. So this scenario is not possible. So this doesn't work. Now I want to think about if it is possible to have, so I considered 1 up, I considered 2 up, I considered 3 up. Now I want to consider no up. So what happens if they are all down? Does this scenario work? you would get a total of minus 3 mu 0. To get plus 3 mu 0, you would need here plus 6 mu 0. Is there any scenario in the second system, the prime system, that will give me plus 6 mu 0? If both are pointing up, I can get a maximum of 4 mu 0. So this also doesn't seem to work. So therefore, I find that there are only 5 quantum states that will give me the required scenario. So out of 32 possible quantum states, because I have this restriction, the total energy must be minus 3 mu 0 b. 5 of them are accessible to the system, satisfies the restriction that is given by the external magnetic field. Okay, so if I specify the probability of quantum states, that means we know the probability of any parameter of the system having a certain value, mean value, standard deviation, etc. Because for each quantum state there is a corresponding macroscopic state of the system that gives me a measurable macroscopic parameter. So this is something I would like to put here as a remark. If we specify the probability of quantum states, then we know the probability of any parameter of the system having a certain value, because corresponding to each quantum state we have a certain value for the macroscopic parameter. For example, for this example 2 that we considered, there are 5 accessible quantum states out of 32 states. So given that you have an external magnetic field B, what is the probability that the total energy of the system will be minus 3 mu 0 b? Well, you look at the accessible states corresponding to this scenario. There are a total of 32 accessible states, and 5 over 32 would be the probability of having this energy. If the system is known to have this energy, then these will be the accessible states to the system.